Let's say you have 79 squared, and you want to find a faster way to solve it. The first thing that comes to mind is evaluating the power to 79 times 79. But now, you have this messy product which will be difficult to solve. So let me show you a general rule. A plus b whole squared equals a squared plus 2ab plus b squared. Why are they equal? Let's try to simplify the left-hand side to the right-hand side. First, we have a plus b whole squared. First thing we will do is evaluate the power, so the expression becomes a plus b whole times a plus b whole. Next, we will cross-distribute the factors, which means FOIL a times a is a squared. A times b and b times a are the same, so ab plus ab or 2ab. And b times b is b squared. And would you look at that, the left-hand side does equal the right side. No additional stuff, just pure algebra. Apply the same to 79 squared. 79 can be rewritten as 70 plus 9. This is of the form of this trinomial. Substitute a equals 70 and b equals 9. We get 70 squared plus 2 times 70 times 9 plus 9 squared. 70 squared is 4,900. 2 times 9 is 18. Times 70 is 1,260. And 9 squared is 81. Adding them together gives 6,241. And thus 79 squared equals 6,241. Now, while the trinomial is useful for all squares, there's a hidden ending in a 5-square shortcut. And it has something to do with any number n, and then multiply it with the next natural number, then stick a 25 at the end. Let's try an example. Pick a number that ends in a 5 like 65. You would take the 6 from 65. Then multiply it with the next natural number, which is 6 plus 1 or 7. And 6 times 7 is 42. Last thing is stick a 25 at the end, and you have 4,225. So 65 squared equals 4,225. But the problem with this is that even though we got to the correct answer, it doesn't specifically follow the math rules. The thing is, you can't just stick a 25 at the end, because mathematically 42 and 25 can never make 4,225. So how can we transform this to pure math? This is not the only error. There's another one. You can't just split 65 to 6 and 5. Same broken rule, not following math rules. If we follow the trinomial rule, by substituting a equals 10, where 10n came from the tens place for any number, and b equals 5, we get 100n squares plus 100n plus 25. But look at the first and second term. They both have 100n in common, so factor it out, and we get 100n times n plus 1 whole. This equality exactly fits into that ending in a 5 shortcut square we were talking about. Instead of saying, do an n plus 1 whole, then stick a 25 at the end, we first say, do n times n plus 1 whole, then multiply 100 and then add 25. This showcases the equality for 100n times n plus 1 whole plus 25. Now, you might ask, are a plus b whole squared and 100n times n plus 1 whole plus 25 the same thing? Because if we substitute a equals 10n and b equals 5, the equality holds. But that's only if you substitute the variables a equals 10n and b equals 5, which does make the equality true. However, if we didn't do the substitution, the relationship wouldn't make sense, because a and b does not compress to a single variable n. Also, we already established that a plus b whole squared is a squared plus 2ab plus b squared, just by using pure algebra, evaluating, distributing, simplifying, and that's it. So it seemed the ending in a 5 shortcut wouldn't make sense for the base. But let's assume a plus b whole squared were to equal 100n times n plus 1 whole plus 25. If that were the case, then that also means a squared plus 2ab plus b squared equals 100n plus n plus 1 whole plus 25. To make things less confusing, we will distribute 100n into n and 1, so both sides have 3 terms. Now let's observe the sum in both sides. assume a squared equals 100n squared, and 2ab equals 100n, and b squared equals 25. Now let's simplify three equalities. 100 is a perfect square with is 10 squared, and since both are being squared, we multiply the bases, so 10n whole squared, then we cancel the exponents, and a equals 10n. Similarly, for b squared equals 25, 25 is also perfect square, which is 5 squared, cancel exponents, and b equals 5. Now for the final part, 2ab equals 100n, and we already established two equalities. If we substitute, we get 2 times 10 and times 5 equals 100n. 2 times 5 is 10 and 10 times 10n is 100n. The equality holds, but there's one thing we're missing. We aren't actually proving they're equal, we actually did algebra instead of visual proof. Meaning, for the equality to actually be true, the solutions have to be a equals 10n and b equals 5. This is not a valid way to prove they're equal. All we did was just find solutions. So instead of visual proof, we actually did algebra, which wasn't even needed for the proof. But even this is not the full proof. Consider two squares. One that ends in a 5 and one that doesn't. If we solve these two squares, the arguments are different. For the one that ended in a 5 thinks the equality should be true, but the other that didn't end in a 5 said they are unequal. No one will argue with me that saying they are equal, but also not equal, doesn't make sense. So is there no well-defined interaction between both sides? Let us dive deeper. If they have to be equal, they must end in the same spot. But substitution of natural numbers. Let's start with left-hand side. If we plug in any natural number for a and b, it seems to output any natural perfect square. But if you try to do the right-hand side, you only get 10% of all squares that end in a 5. For example, 5 squared, 15 squared, 25 squared, and etc. Here is a substitution graph for both expressions. Just by looking at the two graphs, you can obviously see the difference, one having all green, but the other has 90% of all red, indicating some squares don't work in that expressions. This contradiction is another reason why their interaction can't be defined, because of two mixed arguments between two expressions. That's not all though, we also have to consider coordinate graphs where we plot values. We all know a plus b whole squared produces any squared number, and the ending in a 5 shortcut 1 produces 10% of it. If we find the y quotient of 110, we get 101, and this 10 is a factor between two linear x lines that output the value for y. If they overlap, they are equal. But look, the right-hand side actually grows more than the left-hand side, indicating they are not equal. The problem with the two arguments is that since they both may or may not work for the relationship, we can't determine which actually best fits the bridge, so it's not just undefined, it's indeterminate. Without visual substitution to build the bridge, we can't find what goes between those. Therefore, the verdict is that there is no interaction between both sides.